In this video, we're going to discuss bond dissociation energies. So we've talked that potential energy is trapped in bonds between atoms. So as you've got some positive charges of your protons, your negative charges of your electrons, as your atoms get closer together, those electrons end up in the middle, and both protons can be attracted to the electrons from neighboring atoms. The result of which is there's a force pulling the two nuclei towards each other. They're both drawn to where those electrons are in between them. Now, if they get too close, the positive charges will repel, but for a while, there is a best distance you can get. Now, if you've ever had magnets get near each other, they start pulling closer and put a little force, and you can pull them away. But if you let them get close enough that they touched, you got to put in more work to pull them apart. The closer charges are together, the more work you have to put in to separate them. This is more energy. Well, when charges get near each other, they give off that energy. So if you have two magnets and you're holding them, they're not doing anything, you let go and they pull towards each other. They turn their potential into kinetic in order to get closer, which means they give away that energy when they finally meet. Now, you can hear the noise of two magnets slamming together. The vibrations and of all the kinetic is given to the air molecules around them. That energy is spread out. Similar things happen in atomic systems. You tend to give away the energy as light and as heat. But as the nuclei fall into these bonds, they give away their potential in the forms of thermal and kinetic. Well, there's an interesting property, and it is state function. It's a fancy term that basically says we only care about the start and the end. If you are asked the question, how far between point A and point B? The green line shows us that distance. But if you're driving somewhere and you kind of go over to the store, say you take some work and you go around, you eventually reach your second spot. You might have traveled many, many, many times farther than the distance between A and B, but the question we asked is still just, what's the distance between them? Your route is irrelevant to a state function. It just cares what's the difference between your start and your end. Where this comes up, it's things like how much money do you have? If you had $20 and then you lost 5 and went to 15, and then you gained 6 and went to 21, and then you lost 17, and you went to 4, and then you gained 32, and you went to 36. Well, at the end of the day, the difference between where you started and where you ended is 36 and 20. The difference is 16. None of those other values actually matter for what's the difference between start and end. They are the path you take, but the start and the end is really what we're going to be concerned about here. This is true for the energy in bonds as they rearrange in reactions. You have to put some energy into break bonds, you get energy back as you make bonds, but in the end, it's only the difference between the start and the end that matter. Why this is really handy for us, let's take a minute and think of this. Methane, 2-dioxygen, goes to CO2 and 2 waters. Delta H of this reaction is negative 213 kcal. Burning, fire, the oldest harnessed chemical reaction humanity has. In fact, we harnessed it before there was a humanity. Our ancestor species have been able to do fire, and we don't know how this reaction works. We really don't. Methane or anything burning, we don't know how it gets to carbon dioxide. We think things like one of the hydrogens might break off from initial heat. You might have dioxygen around, and that electron that is no longer paired jumps and breaks one of the bonds of dioxygen. And so you might end up with a bond here, and then oxygen will have that unpaired electron. This may break off. It may run into another intact CH4. There's all sorts of things. We don't really know. We know that there are many, many, many steps to actually accomplish this. There are so many and so varied and so short-lived, we can't identify them. So we don't even know what the path that the atoms take to rearrange actually is. But it doesn't matter. We know where we started. We started as methane and dioxygen, and we know where we end. Carbon dioxide, water, and some energy. If you were to imagine the potential energy of your molecules, we know that CH4 and O2 collectively start higher than our products, CO2 and water. Because what happens is when the reaction happens, we go down in energy, giving that away to the rest of the universe as heat. The potential energy that used to be in the bonds has decreased and was released in the reaction as heat. How we got from start to end is irrelevant. The true path could go up. I mean, you have to light methane on fire. It doesn't just do it on its own. It could have gone down a few steps, up a few, down, could have gone way down, jumped back up. We don't know what path it took. But in the end, the start and the end have to be the same regardless of the path. This is the power of state functions, and chemical changes of reaction are state functions. The energy involved with them has to be exactly what the difference between the start and the end is. This means we can invent our own path. We don't have to follow any real path. We can just pick one that's really easy. So let's try a slightly different reaction here. Let's try H2 plus F2 makes 2HF. Less bonds to deal with. I could invent a reaction path that says, hey, my hydrogens, let's break them into just 2 separate hydrogen atoms. My fluorines, let's just break them into 2 separate fluorine atoms. And then if I have an H atom and a fluorine atom, I can pair them and turn them into HF. And I can do that twice. I've made a reaction where the steps are actually very simple. Reality is it's probably nowhere near this simple, but again, the path doesn't matter as long as I end up in the same spots. So this simplified path is something we could draw. I have my H2, I have my F2. I could imagine putting in the energy to break them. Pulling atoms apart takes a little bit of energy, so I had to raise their potential. It had to be higher. Then I can bring those atoms together and let them react. What will happen is, as they react, like letting 2 magnets pull towards each other, they'll get closer and they'll give off energy as they do it. And you will make 2 HFs. Now the question is, does it go all the way down to lower than the start, or does it only go a little bit down and it's actually higher than the start? Well, if you knew the energy for those individual simple steps, you could calculate it. And conveniently, those individual simple steps are rather easy to calculate. If you have dihydrogen, you can shine a laser at it. Photons are a form of energy, and bonds tend to absorb them really well if they're the right energy to excite the electron. So you shine a weak laser at a bond, and if it's too weak to break it, the bond doesn't break. But you can turn your laser up, make it stronger, make it stronger, make it stronger. Eventually what will happen is your laser will have enough energy to break the bond. When that happens, if you know what energy your laser is, you know the energy to break that bond. And so we can actually calculate these fairly easy. Lasers, they're wonderful things. What we find is that for H2, it is 104 kcals per mole to break it apart. For fluorine, for difluorine, it is 38 kcal per mole to break it apart. And if you have HF molecules, you can break them apart. Shine light, crank up the laser until it breaks them. This is 136 kcal per mole to break. Well, if I want to break HF apart, I'm just doing the reverse of forming it. To break a bond requires us to put in energy. If you form a bond, it gives away that exact amount of energy. So the fall from free atoms to HF is giving away 136 kcals. If you're going from the bond to free atoms, it is adding in 136 kcals. These are reversible. You just change the sign. Anytime you form a bond, you're going to give away energy. Anytime you break a bond, you're going to put energy in. Well, this lets us approximate what the reaction will have. What is my delta H of this reaction? How much energy will actually be given off when my H2 and fluorine react to make 2HF? I can say, well, I have 1 mole of H2, so my H2, 1 mole of it, is going to require 104 kcals to break apart. Same with my fluorine. I have 1 mole of F2. I have to put in 38 kcals to break my F2s apart. Then I have 2 mole of HF. Well, this is going to be each of them. I'm forming my HF. We said we took our free atoms and we were combining them to make our product HF. So this is going to be minus 136 kcal, but I have 2 of them, so I do it twice. 136 kcal. Those free atoms that we created, when they come together, they're going to give off energy. And so the atoms will lose the 136. I'll add these together. 104 plus 38 minus 136 minus 136 for a total of minus 130 kcal. We can approximate. This isn't a perfect value, but it is very close. Our delta H of reaction is going to be minus 130 kcal. Now, why they're not perfect, depending exactly on your system, this can vary a little bit. If you've got more complex molecules, they can be pushing each other out of position, so the bond energies we gave here, these are averages based on many, many tests. But this is generally the case. So we can approximate to a very reasonable degree the energy of the reaction, the delta H at least, the enthalpy of reaction. Test this again. Let's look at a slightly different set of reactions. This time let's do H2 plus I2 going to 2HI. We can determine the delta H of this reaction. What I need to know is that H2 has a bond dissociation energy, that's the energy to break it apart, of, as we saw before, 104 kcal per mole. So bond dissociation, the energy to dissociate the bond, to break them, pull them apart. I2 also has a bond dissociation energy, and for I2, that is 36 kcals. Not particularly different than when we were looking up here for fluorine. It's H2 again, so that's the same. FF bond was 38, II bond is 36. They're not terribly different so far. But the HI bond is quite different. It has a bond dissociation energy of 71 kcals. We can invent our own path here again. We can say there's going to be some energy. I'll have some starting material, H2 and I2. I'm going to break them apart into two HI atoms and two H dot atoms and two I dot. So free atoms. My question is, does it go down a little or does it go down a lot? Go ahead and pause here. See if you can calculate. What is the change in energy? What is my delta H of reaction? All right, if you gave it a shot, well, I had plus 104 kcals from the H2 breaking. I had to put in that much energy. I had plus 36 kcal from breaking the I2. But when I form HI, I'm going to give off the bond dissociation energy. If it takes 71 to break it, it must give off 71 when it's formed. So minus 71 kcal. And since I have 2 mole of them, I do that twice. In this case, we will get a difference of minus 2 kcal. So we do end up going a little below our starting. We dropped a little bit down because at the end we had a little bit less potential than we started with. We had 2 kcals less. So our 2HI are down here. That very slight difference between our start and our end, highlighted here in green, that is our delta H. We went down 2 kcals, and so our delta H of reaction is negative 2 kcal. HI bonds are not nearly as strong as HF bonds, and so forming them didn't give off nearly as much energy. As a result, while we did end up slightly negative, it wasn't really all that much. Our products have nearly the same potential energy as our starting materials do. But this is where the energy in these reactions actually is coming from. The delta H of reactions aren't arbitrary and from nowhere. They're built on the rearrangement of the bonds between the atoms in the molecules. So if you have something like CH4 and O2 going to CO2 and water, then what you really have is 4 CH bonds, 2 OO double bonds. Over here you'll have 2 CO double bonds and a total of 4 HO bonds. If you knew the bond association energy for all of these, you could calculate out the energy that has to go in to break these, so positive amounts to go in, and the energy that comes out when you form your products. The difference between them will be the delta H.